Hello everyone, hope you're doing so well. So in this session, welcome back to my channel, Keep Learning Your Study Partner. So in this session, I'm gonna share you regarding the steam power plant generation. So in this case, I will simulate the steam power generation using the our free license software simulation, that is DWSIM. Because it is free license, and then you can open my previous video how to download it and install it in your personal computer. Okay, prior to simulate our steam power generation, I will redraw it for the conceptual study first, because it is very important to see how it can be worked with the steam power generation. Okay, so basically the steam power generation is construct with if the steam power plant. So for the power is generated from the steam, like the STG, steam turbine generator. So basically we have the one of the famous cycles in the power plant. So here we have the BFW, or boiler feed water. Okay, I will give you a brief explanation regarding this one. So the BFV will pump it to the higher pressure. Maybe is for the suction pressure is around, let's say, 1 atm or 1 atmospheric, and then we have to pump it with the 45 bar G. Okay, and then we have to put it some heat generation in here. Maybe we can say it as a boiler, or we can say it's SRG, heat steam recovery generator. At SRG is basically come from the GTG, because it will utilize the excess of the heat from the GTG, and then we can transfer it to this heat exchanger. Okay, this around maybe 40 degrees C, 45 bar G, and then heat it up till it maybe around 40 degrees C, because it's just boiler is just convert the water to steam saturation. So I'll consider it the fixed pressure in here. This is 45 bar G. And then we have also steam turbine in here. You can also combine it for the HP steam turbine and LP steam turbine in here. And then you have also condenser in here. And then you have to make up water maybe if you need it. So the HP or LP steam turbine or steam STG, steam turbine generator, is basically convert from the high enthalpy to the low enthalpy with the exact sum of amount of the work in here. and then this work will be converted to the power as well. So maybe the outlet for the LP steam turbine is around maybe guess 100 or until 120 degrees C, and then for the pressure is around maybe 2 bar G. Okay, and then it will condense until this will pass it to saturated point, and then it full the subschool of the water. Maybe it's around, okay, if we consider the pressure drop in here, we have to put it 1 bar G for the pressure, and for the temperature is around maybe is 70 degrees C. Okay, so this basically how the steam or STG will work with this scheme. Okay, and then I will simulate it this cycle with our free simulation, DWSIM is this free license. Maybe you can also use Aspen Hysys, because if you are using Aspen Hysys, maybe you can generate more precision for the results, because the Aspen Hysys is very good rather than DWSIM, because Aspen Hysys is you must pay for some license, because, and otherwise for the DWSIM is this free license. Okay, I will share for the worksheet simulation. Okay, after we're finished for the conceptual study design, as we can see in our previous scheme, that we have to simulate it to our worksheet using DWSIM process simulator. Okay, if you didn't have for this software, maybe you can check my previous video and then you can download and install it as well. Then we have to create new in here. Okay, since we have to simulate also the steam or this water, is very simple. Then we can type it as the water here, and then you can check in the chat box and click next. So it is for a lot of for the property package, but I will use for the simple one for the steam table, because we need to ensure that our simulation will go through with just the water. For the component, is the only component is the water, so I will use the steam table in this simulation. Click that and go to the next. And for the system of unit, I will select for the C1, because the C1 is claims for it is familiar for our industrial standard, like for the different pressure. You can see this for the kg force per centimeter square, and then density is also the kg per meter cubic meter, and the volumetric flow is the cubic meter per hour, and for the mass flow rate is kg per hour. Click finish. I will add for the first material stream in here. Okay, I will change the name with the BFW. BFW inlet. I will keep it as the horizontally inverting because we need to ensure that it will good for the appearance. And for the temperature, I will use as 35 degrees C, and the pressure is just about 1, or maybe I will put it as the 1.5 kg. Or just keep it as the 1 atm. Okay, I will use for the 10 tons per hour for the steam mass flow. Okay, for the property package is correct as steam table, then you can check it as the last run executed time has been successful. I will put the pump. As we can see, we have to pump it the BFW to the higher pressure, so we need to install the pump in here, pressure changers, and click for the pump. Okay, I will reconfigure that the inlet stream is BFV inlet, and then the outlet stream is number 4, and then I will invert it horizontally to make it good in view. Invert horizontally also. Okay, for this one I have to this the calculation type. You can also select the power required and stream performance curve, but in this case I will select for the outlet pressure because we need to change it, the outlet pressure till to 45 kg. Okay, it is convert, and then the efficiency I can assume as the 75. For the temperature is a slightly increase, maybe it's just a little bit, and then after we are pumped for the FW inlet, so we have the high subscale water, high pressure of the subscale water in here. This is the BFV outlet. Okay, and then I have to put off the heater or boiler because in this DWSIM the boiler is not found, and then it is not provided in this simulation. You can also use for the heater in here, heat exchanger heater. Okay, but if you are using for the Aspen HYSYS, you will find the heater. Okay, for the heater, the outlet of the heater or boiler is the BFW outlet, because we need to increase the enthalpy or the enthalpy of this stream to the higher one. With put some the heat supply for the fuel in here, so so finally we have some the high pressure and high temperature of this stream. We can also generate for the outlet stream in here. Okay, so we need to answer that calculation type. I will choose the outlet temperature because we need to specify it first. Maybe the pressure drop you can mention also is 0. Is maybe you can also put the 0.1 or 0.4. It's up to you because it's very important. And then I'll put the pressure drop is equal to 0. The efficiency, I just assume that the 100%, and the outlet temperature is maybe around the 40, 45. Okay, 450. Okay, I think it's okay. Then you can see the outlet vapor pressure has been changed to 1, because it's previously in to be 0, and then it is currently to be 1, because as you can see this, it will expected that the stream number 7 is in this full of the steam in here. So this is the high pressure and high temperature, and the enthalpy will be high also. Okay, I will rename it as a heater or STG fit. Okay. Okay. And then if we have simulate for the STG fit, because it's very high enthalpy, you can also see in this one the specific enthalpy around the 3000 kg per kilogram. Okay, and we can put for the turbine in here or expander. Maybe if you are using the Aspenesis, you will find for the turbine, not expander. Okay, in this case I will use for the single turbine, or we can add it as the HP and LP turbine is based on your simulation objection. Okay, the STG, the outlet per stream, is stream number 11, and then the calculation type I will check it. Okay, for the outlet pressure, the thermodynamic process is adiabatic instead of the polytropic, because adiabatic is, I know that if the adiabatic is the ideal one, it's not realistic, but it's okay to is just simulated. And then the outlet pressure, maybe I will add it as the 1.8 kg in here. Okay, then you can see the power generation is around 1529 kilowatt. Okay, for the stream number 11. Okay, you can see that the vapor mole fraction is still to be 1. It is indicated that this stream is only in the saturated steam or just superheated steam, because the temperature is above 100 and the pressure is 1.8. Okay, and then we have to reduce this enthalpy till the subscooled steady state, because we have to recycle it to our pump, BFV double pump. Okay, so I'll rename it for the stream number 11 first. This is the STG outlet. Okay, and then we have to add some condenser here, because we don't have any condenser, specific condenser I mean. So I think we have to, okay, that's air cooler, but is the Pro, this Pro we have to pay it first. So I will use the color in here. Okay, I will disconnect it first because we have to ensure it will be converged first. Okay, I will disconnect it. Okay, and then I will put new stream in here and make it invert horizontally. The outlet stream is number 13. Okay, and then as you can see, the calculation tab is hit edit or remove it. I will change it to the outlet temperature, and the pressure drop maybe is just 0.1 kg, and then the outlet temperature is 30. Okay, it's okay. I think 35 is okay. Okay, that's good. This is comfort. So finally we have to put it or reconnect it, the stream number 13 to stream for the BFW inlet, but you need more attention in here, because if you directly connect it to stream number 13, the BFW inlet, you will not your simulation will be not in converge, because the calculation is the trial and error calculation if you put it the stream number 13 to BFW inlet. So to ensure that your simulation has have to converge, you need to put the logic block in here. So we need to add the logic block as a right cycle block in here. So the main function of recycle block is to reiterate and then give us some limited of your calculation, that your calculation is not going to infinity the calculation. Okay, and then we have to put, I will disconnect it, and then I will put it to the BFW. Okay, I will delete it. Okay, you can solve the flow sheet. Okay, that's done. As you can see in here, so for the summary, we have the one cycle of the power plant, steam turbine generator power plant. We just only use the one single turbine, the HP single turbine. Then you can see as for the stream number 15, the vapor phase mole fraction is become 0 because we condense it until to the subcool state, and then this is the water, not the steam again. But if in the STG outlet is also the saturated. Okay, I think it's done. So finally we have the power outlet around 1529 kilowatt, is around the 1 megawatt. Yeah, I mean, with the steam 10 ton of the steam and 10 ton of the mass flow. Okay, I think that's enough for our simulation. So if you have any question or you have any something to discuss with me, please don't be hesitate to contact me through the LinkedIn. You can catch me on the LinkedIn with David Wayu Permadi, and we can discuss for this same turbine power plant. Okay, thank you for your attention. See you.